well, I join all of the other speakers in being delighted and grateful for being in this wonderful workshop. And today I'm going to talk about how do we, or some perspectives of how we transition these quantum technologies from the lab and from a relatively low TRL or technology readiness level to deployment or to industry or at least a higher TRL. And I'll do that from the perspective of quantum communications, which is my field and what I do. So first, let me set the scheme a little bit. So this is a very, very, very rough, so don't take it too seriously, timeline of quantum communications or quantum networking technologies. So at the top, we have some applications, and at the bottom, some of the enabling technologies or enabling breakthroughs, trigger points that might enable the things on top. And I've highlighted 3 applications there, starting from today, to a medium-term application and then maybe to a longer-term application. So today, something we can do today is what we call trusted node quantum key distribution, which is a form of quantum-safe encryption. In the medium term, we can do trustless communication. And Arthur set the scene very nicely, actually, because what we do for that is to rely on distributing entanglement. So if we distribute entanglement, it doesn't really matter how we do it. We can test that entanglement is enough. The fact that something violates a Bell inequality means that we do not need to trust the intermediate steps that have happened in that distribution. And finally, in the very long term, we have applications connected to quantum computing, like secure delegated quantum computing or blind quantum computing. And of course, that necessitates the appearance of a quantum computer, so that will take a little while. And at the bottom, again, we have some enabling technologies. Now, one thing that I always feel lacks in these timelines, especially for quantum networking, is that we need another axis in the description. It's not enough to say we can distribute entanglement, for example, but we need to be able to say, okay, how far? Where is that getting? It's not the same to distribute entanglement inside my lab than it is to distribute entanglement at a global scale. So we need a sort of a space-time diagram. So this is my attempt. I'm still looking for a better representation. So if anybody has an idea, let me know. But on the y-axis there, you have a sort of a logarithmic scale of distances, 10 kilometers, 100 kilometers, 1,000 kilometers. And they roughly represent what would be a local area or inside, say, a data center, inside a facility. That would be like a 10-kilometer scale, then a metro scale for 100 kilometers, and finally a global scale, order 1,000 kilometers. So we can see that there are technologies in quantum networking, or applications, I should say, that are available today and have a relatively high gradient, steep slope into getting to a global scale. A good example is quantum key distribution. We have commercial quantum key distribution, and there have been demonstrations of a global distribution of keys notably by the Chinese satellite missions, right? Then for distribution of entanglement, of course, we can do some distribution of entanglement already, but it's not exactly commercially available, and it's going to be harder to do this at a global scale, so we have a less pronounced slope, and so on and so forth. Again, take the time scale with a huge grain of salt. And also, of course, some applications might not make sense to have at a global scale. I don't know that we need to have secure delegated quantum computer at thousands of kilometers of distance. Probably it will be a shared facility in a metro area or something of that sort. All right, so there's some different perspectives that we need to consider when we solve problems from the point of view of academia and the point of view of industry. And I'm just cherry picking a few things here. But in science and academia, and I've been an academic for most of my life, we love general solutions, right? We love starting a paper or starting a statement with the general solution to this problem is blah. That's not always the best approach in industry. We often want a concrete solution to a well-defined problem, and trying to look for generalities might just slow us down or make the problem too complex. In academia, we also love by necessity hero experiments, which are often monolithic. So in our attempt to show the latest effect and get the closest to the edge, we do these experiments that really only have to survive for as long as we have to get the data. I mean, as long as we can get the data, the experiment can self-destruct at the end of the run. Of course, that is not the case in industry. We have to think from the beginning about modularity and scalability. These are critical things. There is also another aspect, which is, again, we love absolute proofs. We love to say things like, this is unconditionally secure. And the quantum security has been particularly, let's say, guilty of this. Of course, security in practice is evaluated based on threat models and what is the cost of failure, and just generally as a reduction of risk strategy. You want to reduce the threat envelope of what you're doing. So just to summarize, general is often not a good path to implementation. I think this also reflects the discussions we were having in the last few days about error correction versus error mitigation in NISQ devices. So I like to think of the NISQ era as sort of map it to the Anna Karenina principle, which says that all happy families look the same, but each unhappy family is unhappy in its own special way. And you can think of NISQ devices the same way. All universal quantum computers are the same, but all NISQ devices are different in very special ways. So when we think of techniques to reduce errors or so on, there might be huge advantages to thinking of the specific error models and how do we suppress those rather than a completely general error correction scheme. Same thing in the context of quantum communications. It is often said that QKD is not a general solution to the quantum vulnerability problem of the public key infrastructure, PKI. And that is absolutely true. It is not a general solution, but that is not a reasonable standard. Does it provide something that is useful in some context? And just to conclude, we like to often think of approaching problems with a Unix-like philosophy. So we want one tool that does one thing really well. And that allows us to do things in a modular way and a scalable way. All right, so let me illustrate some of these points with that application that I highlight there, which is trusted node QKD, which is really one of the, I would say, most mature quantum technologies that we could conceivably think of scaling or deploying. And it serves as I think, as a good example for this. So first of all, what is QKD? There are many protocols, from BB84 to E, which is Eckert, by the way, sitting there in the corner, 91, and so on. What is it? It's a way to generate shared private randomness. And shared private randomness is a really powerful resource. It's an element of a cryptographic stack. Not the full cryptographic stack, but it's an element. And it's an informationally secure method to transfer or to share keys. And by informationally secure, we mean that there is a positive proof of security. You can write it down. According to the assumptions of a protocol, you can prove security. Now, it complements post-quantum cryptography for a defense in depth strategy for quantum resistance. And I put that squiggle especially yesterday night, given the discussion we had before and the comments from Matthias. It is a complement. QKD cannot do the same things that PQC can do, but that is not, that's not the discussion. It's just another element. When we talk about defense in depth, what we mean is that we layer security, and this is commonly done, and has nothing to do with quantum. This is done in classical security. We layer security in different ways, and ideally what we want is that the failure modes of those different layers are as different as possible and as non-overlapping as possible. So when you talk about post-quantum cryptography, which is an algorithmic security, complementing sometimes with a physical security layer like quantum key distribution might make sense. And a final note there, QKD security is independent of advances in computing or cryptanalysis. There is a positive proof of security, and therefore that's not relevant. All right, so this is the application. So let me highlight some concerns that often get made out of about QKD, and this is both in academia or primarily in academia. So I'll just list them. It's often said you need a dense network of trusted nodes, which is problematic, right? It sounds pretty terrible. And the maximum distance is 100 kilometers. How are we going to do this? Doesn't make sense. We need or strongly prefer unamplified dark fibers. There's a lack of standards. There is a lack of hardware interoperability. And it's hard to do the hardware-software integration. Key management systems don't exist, et cetera. The kind of concerns we look at first in a place like where I work at AWS, so a large cloud provider, are what is the reliability and resilience of the systems? What is the operational readiness, which I'll refer to as the other interoperability? What is the supply chain readiness? Are there choke points in the supply? Are we going to deploy something that cannot be properly maintained? I already mentioned this. What is the performance across distance scales from local to global? And finally, legislative concerns. Are there going to be problems deploying this in different places? So let's talk about that first one. We need a dense network of trusted nodes, and the maximum distance is 100 kilometers. Those are both true statements. It sounds very problematic if you need to go to large scales. But the right question to ask is, what does a hyperscaler network really look like? What drives the structure, and how is it evolving? And for that, I need to talk a little bit about what the network of a place like AWS looks like. So first of all, AWS has one of the largest fiber networks in the world. That's how all those data centers communicate with each other. And it's structured in a very definite way. I'm going to almost say it's fractal. Sorry, that was a fantastic talk, so I wanted to refer to that. So what we have, well, everybody has, or all hyperscalers have this. We have regions, which are typically located in one country, because sometimes there are data residency concerns and so on. So we have a region, and usually your computation and your data stays in a region. Within a region, we have availability zones, which are independent clusters of data centers. And within an availability zone, you have several data centers. And these things are structured like this for very definite reasons. And there are two competing components. So one of them is that the data centers cannot be too far away from each other, because people care about ping time. You can thank gamers and streamers for that. You care about the time of your signal going back and forth. And no matter how much we virtualize, even in AWS, physics still matters. And if the data centers are too far apart, your ping times are inevitably constrained. So that imposes a limit on how far things are. And you can look at public ping times and sort of figure out how far the data centers are. But what you will see is that within a region, actually the 99% of the distances are within 100 kilometers. So that 100 kilometer distance is maybe not as relevant as it seems. All right, the density of the network. Of course, these networks are getting denser every day. I think, well, I don't remember how many regions got launched this year, but there is a data center set up more or less every week, just in AWS. So these little nodes are sprouting everywhere, and everything is getting denser. And these data centers already behave as trusted nodes in many senses. So that part is not that concerning. Now, just a note, of course, that network I put there is sort of the spherical cow version of the network. And if you look at some of the older regions, it looks like an absolute monster. But the main point still stands. The networks are getting denser. and this is not such a big concern. All right, we need or strongly prefer unamplified dark fibers. Well, let's put this in clear economic terms. Amplified fibers are expensive. The distances are not that large, so most of our fiber is not amplified. There's also plenty of dark fiber. You know, at the point that you're running out of dark fiber to connect data centers to each other, you need to be laying another cable. So this is not actually a strong concern. Finally, those lack of standards and lack of hardware interoperability. Well, the question is, where do I really need this? And if you really look at that question, you realize that you, of course, really need the standards and the hardware interoperability at the edges of the network when you're talking to other people, which you should talk to other people, but it's not the majority of your links. Standards matter for two things: for talking to other people and for compliance. So depending on where you stand in these things, you have to do different bits and pieces. All right, and now I'm going to rush very quickly about to tell you a little bit about some of the research that we're doing in this trustless communication task by developing repeaters, and how we're working towards the scalability. So first of all, we are working on the silicon vacancy platform. We actually have a close collaboration with Harvard, with Misha's group and others. So we're trying to improve the material platform, and for that we're collaborating with Element 6, which is a subsidiary of De Beer, so same people, the diamonds people. They have, of course, a division doing scientific diamond, and we're working with them and making a lot of progress. One thing that was mentioned, I think by Carl a few days ago, was that if we're going to do quantum networks, we're not going to have a dilution fridge every 70 kilometers. This is absolutely true. This is not scalable at all. So we need to operate these things at least at a temperature where we can just use pulse tubes, which is an order of magnitude cheaper and simpler technology. And we've made progress in this as well. By straining the lattice, we can actually pull the operating temperature to that regime, and we hope to make more progress in this. Another thing we've done is that often these systems get aligned by nanopositioners in the cryoscale. So you cool down your system, and then you're trying to align a fiber to a diamond chip, not by hand, but essentially by control, by microscopic control. And you do that once you're cold. This is not a sustainable system, first because you can't pack many devices, it's expensive, and also it sort of requires manual intervention. What we want to do is package these things at room temperature and then just cool them down and never have to touch it again. And we've recently achieved exactly this by very carefully gluing our fibers at room temperature. And we have losses. That data point is outdated. It's like 0.4 dB per connection, which is really an extremely nice result. And the final thing I wanted to talk about is operational fit. So it's not just about your devices working and being getting some of these technical things out of the way, but you also need to care about uptime, resiliency, and ubiquity as critical capabilities. And typical questions that we ask in that context are about the supply chain. Can we make enough of these? Is there a single point of failure? Is there more than one provider? Can the devices be installed by non-specialists? If you're going to deploy a quantum network, it's not a single quantum computer. It's many hundreds or thousands of devices. Do they require maintenance? Just to note, not everybody knows this, data centers are largely one-way doors. Whatever goes in never comes out, or if it comes out, it's more or less in the form of Hawking radiation, or the classical equivalent, which is they shred anything that comes out. And can devices fit into a standard deployment model? Are there unusual processes? For example, I'll give you a simple example. QKD systems are often born in pairs. If one fails, it sort of kills the other by proxy because they are aligned to each other. That's not a very scalable way of doing things. So we are checking these kinds of things, meaning we do proof of concepts with external customers, and we try to find the unknown unknowns of these kind of processes. We did a proof of concept in Singapore in the context of the Singapore National Quantum Safe Network. We recently completed something with HSBC and Toshiba and BT in the UK in London metropolitan area. Again, just trying to find out what things break when we do these kinds of things. And with that, thank you very much.